Okay, and now Maarten from KU Leuven.
Okay, hi, I'm Maarten Afschrift from KU Leuven, Belgium, and my talk is about the control of balance during walking. So more specifically, I'm interested in the role of the hip abductor muscles in the control of balance in response to a perturbation. So for this experiment, we had people walking on a treadmill, and we suddenly moved the treadmill to the left. We applied this perturbation during different phases of the gait cycle, as you can see here, and then measured the response of our subject using motion capture, ground reaction forces, and electromyography of the hip abductor muscles. So, similar as other researchers, we found that subjects adjust their foot placement to control balance. And for example, when we apply this perturbation just after left heel strike, we observe an increase in stride width, so an outward stepping, which was accompanied by activity of both the stance and swing leg hip abductor muscles. When we applied the perturbation a bit later in the gait cycle, we still observed this outward stepping, but only reactive activity of the swing leg hip abductor muscle. Then, when the perturbation was applied, when the right foot is on the ground, of course, subjects couldn't use this outward stepping anymore, so they switched to a crossover stepping or inward stepping, and we only observed a small reactive activity of the left hip abductor muscle. So, in conclusion, here in this graph, you can see the magnitude of the muscle response we observed as a function of the onset timing of the perturbation. And subjects seems to change this reactive activity, and they change their foot placement. However, it's still unclear to which extent this reactive hip abductor muscle activity contributes to outward foot placement. And to answer this question, we used a simulation approach. So we used a standard open sim model with 92 hill-type muscles and 23 degrees of freedom. And then we computed the muscle excitations that could track the measured kinematic muscle excitations and ground reaction forces during walking without perturbations, which results in the video you can see here below. So then we want to evaluate the effect of the perturbation force on the kinematics of walking. And therefore, we added the perturbation force to our forward simulation of unperturbed walking, which then results in the passive response, which you can see here in the video in the rat model. Then we evaluated the effect of the hip abductor muscle activity to the foot placement by adding both the measured reactive activity of the hip abductor muscle and the perturbation force to our simulation. We then evaluated our simulations using two outcome variables. So first, during mid-swing, we computed the inter-foot distance, which estimates the risk of inter-limb collision, so when the left and right foot swing beside each other. And secondly, we evaluated at first heel strike after perturbation the change in stride width and margin of stability. So if I come back to this first perturbation, just after left heel strike, where we have this outward stepping and activity of both hip abductor muscles, when we then evaluated whether only stance leg hip abductor muscle activity can explain partially this outward stepping strategy. And as you can see here, it resulted in an increase in stride width. And the mechanism works as follows. So the stance leg hip abductor muscle tilts the pelvis, stretches the swing leg hip abductor muscles, and therefore controls this outward foot placement. And here in this graph, you can see the simulations of all our subjects and all our trials. So every dot is a single trial that we measured. And we found that when the muscle response increased, we found an increase in stride width and an increase in margin of stability, which compensates for the decrease in margin of stability due to the perturbation. A similar mechanism was found of the reactive activity of the swing leg hip abductor muscle. So it also increases the stride width and the margin of stability. And this probably explains, so they have a similar action in the control of balance, which probably explains why we see this huge variability between either using stance or swing leg hip abductor muscle activity between our subjects. So if I come back to this modulation of reactive muscle activity, I already discussed the first one, so that both muscles contribute to this outward foot placement. For the perturbation a bit later in the gait cycle, we see that the swing leg hip abductor muscle activity that we measured contributes to an increased margin of stability. And then for the perturbations late in the gait cycle, so when we observe this crossover stepping, we see that the activity of the stance leg hip abductor muscle, so the left leg, seems to counteract the inward foot placement and even decreases the margin of stability further, but it seems to be needed to increase the interfoot distance and prevent collisions of the limbs. So I think in this study we showed that hip abductor muscle activity is used and modulated to control outward foot placement and prevent interlimb collisions.
Thank you very much for the talk. Just trying to connect the talk, the first talk actually that we saw with the little actuator. So if you think about having this actuator on the lower limb, which kind of controller would you suggest to improve the stability, since we saw that you have this abduction during the walking, or the perturbed walking?
Well, like in this study, I really don't know how this control of reactive hip abductor muscle activity works, but it seems to be that you have to modulate like the amount of assistance you give for hip abduction during the gait cycle, similar as the nervous system does, I think. If that answers your question.
Yeah, maybe you can say something about the timing, or since you're obviously investigating the timing of the perturbation.
Yeah, so. Well, I think you have to be very careful. I only analyze this for this very specific perturbation. So if we talk about this kind of slipping, then I think it's important that you control like this. The swing leg hip abductor muscle activity seems to be very important to control this outward foot placement. So I think then you have to control during this early stance phase perturbations there.
Okay, thank you.
Hi. So you kind of led into my question there. I was wondering what type of perturbations that you analyzed and how potentially like magnitude of perturbation or like origin of perturbation, how that would affect like strategies you observe.
I think it has a huge effect on the strategies that we observe. So I think previous researchers showed very nicely that when you have small perturbations, you mainly use just this ankle rollover strategy. And when you gradually increase it, subjects will switch toward this outward stepping. So it will definitely have an effect on both the kinematics we observe and the reactive activity and so on.
And are these perturbations that you selected kind of like, how did you select that I want to look at this particular size? Was it any?
Yeah, so now we selected the size that triggered the stepping strategy because we are mainly interested in the role of these hip abductor muscles. And we are then a little bit constrained by the actuators.
Yeah. Is that something you would realistically see commonly in, like, is this a type of perturbation that happens?
I'm not sure if it really happens a lot during normal walking, or I think it's just a good way to excite the feedback control system and get some insight in the control of balance.
Thank you.
What is margin of stability?
It's a distance between the borders of the foot and the location of the extrapolated center of mass, which captures both like the position of the center of mass and its velocity. It's based on this inverted pendulum model.
That's pushing it back towards the center.
Yeah.
Assuming it.
All right. Let's thank Maarten.